Welcome. In this part of our series involving the evaluation of series written in sigma notation, we would be focusing on the use of the Moivres theorem. So generally, the Moivres theorem can be used to evaluate series of the form summation from r equals 0 to infinity of sine rx, or summation from r equals 0 to infinity of cos rx. So those cases involving the trigonometric functions sine and cosine. We start by recalling the Moivres theorem. Cos theta plus I sine theta to the n equals cos n theta plus I sine n theta. So you can apply the theorem when the complex number is in polar form or in exponential form. We'll start straight away with an example, a GC equation. Using the Moivres theorem or otherwise, show that for real x, summation from r equals 0 to n of cos rx equals 1 minus cos x plus cos nx minus cos n plus 1x all over 2 into 1 minus cos x, where cos x is different from 1. So to start, we would have to recognize that cos rx is the real part of the complex number cos rx plus I sine rx. And from there, we can apply the Moivres theorem by putting now cos x plus I sine x raised to the power r, which we can then bring in the exponential form as already outlined in the theorem above. The exponential form is very appropriate and convenient to use, especially when you'll be dealing with your calculation of the sum. From there, we proceed to write out and expand the series in order to see how the terms are generated. You will notice that the consecutive terms have a common ratio, and so it is a geometric series in which the first term is 1. The common ratio is e to the ix, that means the complex number cos x plus I sine x, and then the number of terms should be n plus 1. Take again the upper limit minus the lower limit plus 1 would give you the number of terms as n plus 1. From there, now we apply the formula for the sum of a GP, which is supposed to be the first term into 1 minus the common ratio raised to the power the number of terms all over 1 minus the common ratio. And from there, we apply in the formula directly by recalling that we need the real part of the sum as the solution. So the formula, again written in symbolic form, should be the first term, which is u naught, into 1 minus the common ratio to the number of terms, which is n plus 1 all over 1 minus r. And so we proceed to substitute the parameters. First term into 1 minus e to the I n plus 1x all over 1 minus e to the ix. At this point, we need to simplify. Since we are going to be taking the real part, we need to realize the denominator of the complex number, and to do so, we multiply both the numerator and the denominator by the conjugate of the denominator, which is nothing but 1 minus e to the negative ix. We note that to have the conjugate of a complex number that is written in exponential form, we simply take the whole complex number and negate the power of e. And so, proceeding to realize the denominator, we multiply both the numerator and the denominator by the conjugate of the denominator as already explained above. And from there, we proceed to open the brackets at the numerator and at the denominator, so that we get 1 minus e to the negative ix minus e to the I into n plus 1x plus e to the I nx all over 1 minus e to the negative ix minus e to the ix plus 1. From this point, in order that we read the real part, because we are still emphasizing that it is the real part of this complex number that should give the sum that we are seeking to find, we convert the exponential parts of the complex number into their polar form, because it is in the polar form that we can be able to read the real part of the complex number. So that e to the negative ix becomes cos x minus I sine x. Then e to the I into n plus 1x becomes cos n plus 1x plus I sine n plus 1x. And e to the I nx becomes cos nx plus I sine nx. And the same thing applies at the denominator. We replace all the exponential forms by their polar forms. And at this point, we can then read the real part of the complex number, because there is a command here telling us to take only the real part of this complex number, which should then be the real part of the numerator divided by the denominator, which will already become real since we have realized it. At this point, the real part of the complex number would be 1 minus cos x, then minus cos n plus 1x, and then plus cos nx. Those are the terms that are real at the numerator. And then at the denominator, we would have 2 minus cos x minus cos x, because positive I sine x minus I sine x would make that imaginary part to disappear, as the denominator has to become real. From here now, we see that the real part of that complex number would just be 1 minus cos x minus cos n plus 1x plus cos nx all over 2 minus cos x minus cos x, which upon simplification would give 1 minus cos x minus cos n plus 1x plus cos nx all over 2 minus 2 cos x, which already gives the expression that we were seeking to prove. Okay, we take the second example. Using the Moivre's theorem or otherwise, show that summation from r equals 0 to infinity of 1 all over 4 to the r sine 2 r theta equals 4 sine 2 theta all over 17 minus 8 cos 2 theta. This is another GC equation. So we proceed again by writing the complex number in the form that we can use the Moivre's theorem. The first thing is that we need to be strategic here by first expressing 4 to the r as 2 to the power 2r, because we have noticed the coefficient of theta up as 2r, and it will help when we are expressing the complex number in the form that we can apply the Moivre's theorem. And so we recognize that this part is the imaginary part of the complex number cos 2r theta plus I sine 2r theta all over 2 to the power 2r. And from there, the Moivre's theorem can come in, whereby we apply at the numerator cos theta plus I sine theta. You can notice that the coefficient of theta, which was 2r, has been raised to the power according to the Moivre's theorem. In the next step, then, we convert the numerator from polar form into exponential form. Again, as I said, the exponential form is very convenient to work with when you start applying the formula for the sum of the series. So we get summation from r equals 0 to infinity of the imaginary part of e to the I theta all over 2. Since the numerator and the denominator have a common power, we express the fraction to a common power to have this, which can be expanded by writing out the first few terms as the imaginary part of the series 1 plus e to the 2I theta over 4 plus e to the 4I theta over 16, and so on up to infinity. We can then observe that this is actually a geometric progression in which the first term is 1 and the common ratio is e to the 2I theta over 4. When you divide e to the 2I theta over 4 by 1, you get e to the 2I theta over 4. And when you divide e to the 4I theta over 16 by e to the 2I theta over 4, you get e to the 2I theta over 4. So e to the 2I theta over 4 is the common ratio of that GP. And we note that the absolute value of that common ratio, which is a complex number, is 1/4, because the modulus of the complex number at the numerator is 1. So the absolute value of that common ratio should then be 1/4, and 1/4 being less than 1, it means the series converges, and so we can actually find the sum to infinity of the series. The sum to infinity of a GP is normally given as a over 1 minus r, where a is the first term and r is the common ratio. Again, we remind ourselves that we are interested in the imaginary part of that sum. So proceeding to substitute the parameters, the first term 1 and the common ratio e to the 2I theta over 4, we get the imaginary part of 4 all over 4 minus e to the 2I theta when we find the LCM at the denominator. We have to realize the denominator as already explained above in order to read the imaginary part of the complex number. So proceeding to open the brackets, we will then get at the numerator 16 minus 4 e to the negative 2I theta all over 16 minus 4 e to the negative 2I theta minus 4 e to the 2I theta plus 1. And in the next step, we now have to convert the complex number from exponential form into polar form, because it is only in the polar form that we can read the imaginary part of the complex number. So the polar form would be this, which we can simplify to have 16 minus 4 cos 2 theta plus 4I sin 2 theta all over 17 minus 4 cos 2 theta minus 4 cos 2 theta. So proceeding to read the imaginary part, remember again the denominator is already real. So to have the imaginary part of the complex number, we take the imaginary part of the numerator and then divide by the denominator. The imaginary part of a complex number, remember, is usually the coefficient of I. So the coefficient of I at the numerator is the imaginary part, and that imaginary part then should be 4 sin 2 theta, the coefficient of I, and this is it here, 4 sin 2 theta all over the denominator, which is 17 minus 4 cos 2 theta minus 4 cos 2 theta, which gives 17 minus 8 cos 2 theta, and it gives us the required proof. Thanks for watching, and see you in the last part of our series, which will be involving evaluation of telescoping series using the method of difference.